All right, we are live.
Okay. Hi, everyone, and thanks for tuning into this week's Quantum Chaos Seminar. For everyone watching live, I'm happy you found out what the correct time was. So today it's my pleasure to introduce today's speaker, Vedika Khemani, who is currently assistant professor at Stanford University. She did her undergrad at Harvey Mudd College before going on to do her graduate students at Princeton University, followed by a junior fellowship at Harvard University before now being assistant professor at Stanford University. She's probably best known for her work on many-body localization and phases of out-of-equilibrium systems, most notably being Fouquet time crystals. So she's won various awards for her research, including a Sloan Fellowship and an Early Career Award. And so today she'll be talking about entanglement dynamics in non-unitary circuits. For the people who are tuning in for the first time, we really encourage people to ask questions through the chat, which we'll then put to the speaker. So all yours, Vedika.
Okay, yeah, thank you very much, Peter, for the nice introduction and for organizing me and for inviting me and putting together this really nice workshop. I've had a lot of fun listening to some of these talks. So, today I'll be telling you about entanglement dynamics in non-unitary circuits. I'll mostly describe work in this set of papers. The first one is on entanglement dynamics in measurement-only models. This is from earlier this year. And then for the second part of the talk, I'll tell you about a protocol for measuring entanglement dynamics without encountering the problem of post-selection, which I'll describe to you in a specific class of circuits using spacetime duality, and I'll explain what all of that means. Okay, so the second paper is actually really new. We just posted it today, so it should hopefully appear in the archive tomorrow. Both of these works were led by Matteo Ippoliti, who's a postdoc at Stanford, and the first was also in collaboration with Michael Gullen, Sarango Balakrishnan, and David Hughes. Okay, so good. So, the traditional approach in condensed matter physics is that, we search for complex emergent phenomena in many body systems. And for a variety of experimentally motivated and historical reasons, we have traditionally focused on either ground states or equilibrium properties of time-independent Hamiltonians. Okay, so these can be your favorite Hamiltonian, the Ising model, the Heisenberg model, the Hubbard model. And within these equilibrium states, phases of matter are usually defined by studying correlation functions or universal order parameters. And then we study universal properties of these phases and the phase transitions between them. Okay, but of course, this focus on ground states or equilibrium states of time-independent Hamiltonians represents a very restricted corner of the full set of quantum evolutions that we can be talking about, right? And this full set of evolutions includes unitary evolutions very generally. So, they could be unitary evolutions that are generated by a time-independent Hamiltonian, or it could be something generated by a periodically driven or Fouquet system, or even more generally, just by unitary gates, so you can just draw gates that act locally or not even non-locally on various sets of qubits, and these could be drawn from various gate sets that may or may not be universal for quantum computation. Okay, so the most general framework for quantum mechanics is time evolutions generated by unitaries and possibly interrupted by non-unitary measurements. Okay, so that the measurements are also a fundamental part of quantum mechanics. And then instead of considering ground states or near equilibrium states, we can generally consider dynamics from initial states that are not low energy in any useful sense. Okay, there's not even a concept of energy if you don't have, if your Hamiltonian is in general time dependent, right? And then instead of thinking about correlation functions or order parameters, we can think much more generally about different observables like quantum entanglement or quantum complexity. So these more general evolutions opens up this wide new continent for studying many-body physics, many-body dynamics. And with it comes the need to develop a new toolkit, right? And also to think of new paradigms for doing many-body physics. For equilibrium systems, universality and emergence are kind of two central paradigms, but now we're also in search for new paradigms for describing many-body dynamics. Okay. And of course, all of this program has really been driven and has become increasingly important in light of breakneck developments of NISQ devices, right? So these NISQ devices are so-called noisy intermediate scale quantum devices. This is a picture of Google's Sycamore chip, which was recently in the news for an announcement of quantum supremacy. But more generally, over the last few decades, there have been huge progress in quantum simulators in a variety of different platforms, right? And these are new laboratory systems with unprecedented amounts of control and measurement capabilities, which allow us to probe a whole arena of new questions, right? So these questions can take the form of translating questions from the familiar equilibrium statistical mechanics, such as phases or universality, to the out of equilibrium setting. But we can also ask completely new questions about the dynamics of quantum entanglement, the emergence of quantum chaos. There's ranges of questions about simulability of quantum evolutions, either with quantum devices or classical computers, which gets to questions of complexity and quantum advantage, right? So a common thread through all of this effort is the notion of quantum entanglement, and this is what I'll be focusing on in my talk today, right? And the really remarkable thing is that due to these rapid developments, entanglement itself is becoming an observable in the lab setting, right? So indeed, I'll be talking about dynamics of quantum entanglement. So for most of the talk, I'll have in mind starting with some kind of initial state, right? So in general, this could be a pure state, psi naught. The most familiar setting, though I'll be talking about going beyond this, the most familiar setting is time evolving this state with some unitary time evolution operator. This could again be generated by either a time independent Hamiltonian, or it could be more general. It could be this U of t could be a unitary quantum circuit. It could be a random circuit, right? And then you can look at some subsystem in this overall, if it's unitary evolution, the state as a whole remains pure, but you can look at some subsystem of this system as a whole and ask how the entanglement entropy of the subsystem grows in time. Okay, and I've written an expression for the Rayleigh entropies. So you have a Rayleigh index n. N equals 1 is the familiar von Neumann entanglement entropy, but actually for experimental purposes, it's often much more accessible to study the second Rayleigh entropy. Okay, but this won't be so important. This picture that I have here is from this really remarkable experiment from a few years ago in Marcus Greiner's group, right? And they actually performed a measurement of the Rayleigh entropy in a cold atomic system, right? And what you're seeing here is that if they measure the entropy of the entire state, so this was a state with six atoms, if you measure the entropy of the entire state, it remains constant in time. This should really be 0, but the offset is just due to their measurement errors. But so this is saying that the state as a whole is remaining pure because the entropy of the state as a whole is constant in time. But if they look at a subsystem, then they see this growth of entanglement in time, right? And indeed, this is how we understand the process of thermalization or the emergence of statistical mechanics in a closed quantum system, that local observables in region A approach their thermal equilibrium values as a result of the entanglement between regions A and B growing in time. Okay, so another concept that's come out of this enterprise, which will be central in my talk, is the notion of an entanglement phase transition. Okay, so the best known example of an entanglement phase transition probably occurs in many body localized systems. Okay, so this is a phase transition in the dynamics of quantum entanglement. Okay, so something singular happens in how the entanglement of a system grows in time as you cross some kind of transition in parameter space. So, so again, if you have some time independent Hamiltonian, which has a many body localization phase transition as a function of disorder strength, what you'll find is that, within the many body localized phase, your entanglement entropy grows logarithmically in time upon starting from some unentangled product state, for instance. But as you cross over into the thermalizing or the ETH obeying phase, then this growth of entanglement entropy is polynomial in time. Okay, and this is a sharp singular change that occurs. Okay, so this is kind of the first well-known example of a phase transition in the dynamics of entanglement, and in this talk I'll discuss a few more. Okay, good. So the broad scheme of where we are going, right, is a lot of work has been done over the last few years in studying the dynamics of entanglement under unitary time evolutions. Okay, so as I said, these can be time independent Hamiltonians or circuits more generally, and we've understood many features of how entanglement grows universally in kind of chaotic systems, assuming only locality and unitarity by studying models of these circuits, which are sort of minimal models. Okay, so this was really started by this set of papers right here by Adam Nahum and collaborators. Okay, and then this has been where most of the work has happened. Much more recently, we're starting to think beyond these unitary settings. Okay, so one class of circuits that I'll talk about a lot is this so-called unitary projective circuits. Okay, so these are random circuits that are going to be interrupted by projective measurements. A subset of this class of unitary projective circuits are measurement-only circuits. So you'll have, I'll describe what this means, but really you have measurement, you have random measurements generated by random operators that can again come in this circuit form. And this again gives you a very nice landscape of possible entanglement phases and phase transitions. And even more broadly, we can just study quantum circuits that can include weak measurement, decoherence, or quantum channels. Okay, so there's this huge space of evolutions, and we've really only explored very small corners of it, right? And there's a lot of exciting stuff to be done in the next several years. Okay, so I want to come back to this notion of an entanglement phase transition in the dynamics of quantum entanglement. Okay, so you always have, even in thermodynamic phase transitions, say for the ground state of the problem, there are signatures in the entanglement. Okay, so it's not like entanglement across phase transitions hasn't been studied previously, but what I want to focus on is phase transitions in the dynamics of entanglement. And for this, there are very few examples that I'm aware of, right? So there was the MBL example that I talked about. And then, as best as I know, the second example of this phenomena was provided in this set of papers from just a couple of years ago by Matthew Fisher's group. And they were considering this kind of non-unitary system, this non-unitary setting of hybrid circuits. Okay, so these were circuits where you had unitary dynamics, but these unitary dynamics were subject to a finite rate of local projective measurements. Okay, and the question is, what happens to the entanglement of a quantum state under this evolution? Okay, so this is, of course, sort of a minimal model for open system dynamics, okay? Because if you have these measurements, some quantum information is leaking out into the outside world as a result of these measurements, right? And we want to understand what are the possible phases, what are the possible dynamics you can get under this setting, okay? And of course, the initial motivation for this is some kind of competition between coherence and decoherence, right? So usually when we think about measurements or non-unitarity, we have in mind that the unitary evolution is kind of doing the coherent quantum dynamics that we're interested in, and the measurements are coming in from outside and destroying the coherence of the system, right? So this competition between coherence and decoherence, and the question is what should happen in this competition? And of course, the conventional wisdom in this is that decoherence should always win, right? So quantum entanglement is a delicate resource. So you have this highly entangled state, your Schrodinger's cat. But if you come in and you look at it, right, you probe it, you make a measurement, then the wisdom is that this should just immediately collapse this superposition, and you should get some kind of disentangled phase. Okay, so the assumption of what would happen in this setting was that, okay, so when you have no measurements at all, then you just have time evolution under a random unitary circuit that should produce some late time state that's highly entangled. Okay, there's no symmetries, they're just random gates. But as soon as you have some non-zero rate of measurement, then the picture was that these measurements should always win, and they should disentangle your quantum system, and you should be left with some kind of more trivial low entangled state. Okay, but the big surprise from this set of papers was that this doesn't actually happen, and there's a robust volume law phase, okay, for a finite range of measurement strengths, as long as that measurement strength is small enough. Okay, so this is a phase transition in the quantum entanglement properties driven by this rate of making local measurements in your system. Okay, so if your measurements were made at a small enough rate, then you get a volume law phase. Okay, so if I'm looking at the entropy of my system, say of half the chain as a function of time, this will grow in time and then saturate to a volume, saturate to a value that scales as the volume of the subregion that I'm measuring. On the other hand, beyond, if your measurement strength is greater than some critical value, okay, then you get an area law state, and in which your steady state has very little entanglement. Okay, so again, the p equals 0 and the p equals 1 limits of this evolution can be understood very easily. Okay, so p equals 0 means that there are no measurements anywhere. It's just random unitary dynamics that'll go to a volume law phase. P equals 1 means that with probability 1 at every instance in time, you're coming in and you're making a local projective measurement. So say you measure sigma z on every site with probability 1. Okay, so if you do that, you'll collapse your wave function into something which is a product state in sigma z, and that's going to be disentangled. Okay, so the p equals 0 and p equals 1 limit of this phase diagram are very well understood, but actually there's a whole host of interesting questions and mysteries about the rest of this phase diagram. Okay, so first, this is a new kind of critical point in the dynamics of entanglement. From various numerical studies that people have done, this appears to show critical scaling that's compatible with a conformal field theory, and people have been trying to understand where that conformal field theory comes from by considering mappings of these circuit models to various statistical mechanical problems. Okay. There are interesting questions you can ask about this disentangled or area law phase, right? For instance, because the late time states are area law, in some ways they resemble ground states of gapped quantum systems. So you can ask about whether these area law states can host order, these area law steady states can host new types of order, new types of phases. And actually, even in the volume law phase, the volume law phase is itself a mystery. Okay, so this volume law phase is not a generic thermal phase, okay, because the saturation value of the entanglement entropy can be much less than the maximum allowed, because your measurements are gaining some information about the system. Okay, so what one way in which we understand why this transition happens, right, is that in the volume law phase, the system is forming a kind of quantum error correcting code. Okay, and what that means is that you're going in and you're making local measurements, right? But if the information in this quantum state is completely scrambled in very, very non-local degrees of freedom because of this unitary evolution, right, then your local measurements really cannot gain that much information about the global coherences in your state. Okay, so
Vedika, there's a quick question from the audience to clarify. What exactly do we mean by the measurement strength here?
Okay. So in this case, it's very simple. It's just the rate. So this is a random circuit. It's random in time. So at every for every bond, you put down a random gate. But then what P controls is the probability with which you put down a measurement on a given site. Okay. So if P is 1, then you'll go in and so let's say we're doing measurements in the sigma z basis. Okay. So these are local measurements. And let's say I'm going to measure whether the sigma z on a given site is up or down. When P is 1, then in every layer with probability 1, I go in and I measure sigma z on every single site. But with P is 0, I don't measure it on any site. And when P is something in between, then I measure it on average on P times L sites.
Okay, I think that should clarify it. Thanks.
Okay, yeah. Good. So one way in which this volume law phase is understood is in the form of a quantum error correcting code, right? So this volume law entanglement is representing entanglement between different subregions in your system, whereas this external measurement, right, is trying to take this entanglement out of the system by entangling the system with some other external measurement apparatus. Okay, so the fact that you have a volume law phase means that this external measurement apparatus is only able to gain a limited amount of information about your system, right? And the reason it only gains a limited amount of information is understood. So this business of a quantum error correcting code was discussed in these two papers here. And the picture for how this happens is that if your unitary dynamics are sufficiently scrambling, right, then it generates this kind of code in which local measurements are unable to access much information about your dynamics. And then your system remains volume law entanglement despite having a finite range of measurements. Okay, so this is this new kind of entanglement phase transition, and unlike many body localization, which requires you to either have a time independent Hamiltonian or a flow K circuit, this is a phase transition that can occur even in random and time dynamics. Okay, so we're considering hybrid circuit, we're considering random circuits, and they're random in time. And the way you prevent this random in time evolution from becoming highly entangling is by putting in this rate of measurements that competes with that. Okay, good. So one last thing I'll mention before getting to the main talk is that when we're talking about phase transitions in these hybrid circuits, we always have in mind a model for open system dynamics, which is so-called monitored quantum dynamics. Okay, so what that means is that if you have a given initial state, we're always thinking about individual quantum trajectories. Okay, so you have a wave function, and it's going to undergo some unitary evolution, and then you make some projective measurements, and the observer that's making the measurements keeps track of the measurement outcomes, but the state as a whole always remains pure. Okay, so we're not going to average over any measurement outcomes. There's going to be some randomness, because if you go in and you make a sigma z measurement, you can get either up or down with Born probabilities. Okay, but you're not going to average over those up and down outcomes. Okay, and this is different from maybe the more conventional view in thinking about open system dynamics, where you have a system, the system is just coupled to some environment, and the environment is of course constantly making measurements in the system, but the outcome of those measurements is lost to the environment. Okay, so in that case, your pure state becomes mixed. You think about the dynamics of a density matrix, and in general, this density matrix averages over all possible measurement outcomes. Okay, so that's not what we'll be doing here. We'll be following individual trajectories and asking about some ensemble properties of these late time trajectories. Good. So right. So let's let me now just preview the main kind of results of the talk. We may not get to all of that, but that's okay. But I just want to give you a taste of some of the big highlights. Okay. So the first highlight that I want to present is that I'll show you that you can get a third. So I said there were two different types of entanglement phase transitions in dynamics that we were aware of. I want to show you a third example of an entanglement phase transition in what's known as a measurement only model. Okay, so now your random circuits are just going to be different operators. There's an ensemble of operators that you're measuring, and you're just going to plop down these measurements, these operators at different rates. And there's going to be some features of these operators that are going to drive the transition, but this is qualitatively different from the transition in the unitary projective model, because in this class of models, we can see that you can get an entanglement phase transition even with strictly non-scrambling unitaries and strictly one-side local measurements. Okay, so there's no kind of simple limit that you can dial the measurement strength down to 0, and that obviously gives you a volume law phase. This is a measurement only model. And we'll find that this transition is driven by a new kind of variable, which is the so-called frustration of the measurement ensemble. Okay, so it's not this kind of rate of measurements, but it's something intrinsic about the measurement ensemble. And then what we'll find is that there's an infinite class of these measurement only models, those with so-called bipartite frustration graphs. I'll explain what a frustration graph is. It's what's used to characterize this kind of feature of this measurement ensemble, this frustration that drives this transition. And everything with a bipartite frustration graph actually can be shown to display a transition from an area law phase to an area law phase. So it's not from volume to area, but it's from one type of area law phase to a different type of area law phase, possibly with different patterns of order. Okay, so so the first result is that I'll present this kind of landscape of measurement only models and entanglement phases and phase transitions in them. And then I'll talk a little bit about this notion of post-selection free entanglement dynamics. Okay, so I started the talk by showing you Marcus Greiner's experiment on measuring these Rayleigh entropies, right? So it was already a very challenging experiment. But when you have these hybrid circuits where you have unitaries interrupted by measurements, then you actually encounter this very fundamental problem of post-selection that I'll describe that makes any measurement of entanglement extremely hard, exponentially hard. It gives you this huge exponential overhead, which makes it very impractical. So I'll show you that there's a broad class of non-unitary circuits, those that are space-time duals of unitary circuits, for which this post-selection problem can be avoided altogether. Okay. Then, I almost certainly won't have time to get into this, but I just want to advertise it, is that, we have all of these, there've been various talks already in this series, right? So we have all of these notions of how to think about the spreading of quantum information, locality, out of time ordered commutators in unitary evolutions, okay? So in unitary evolutions, there is an obvious notion of locality if you have a local Hamiltonian or you have circuits that are acting with local gates. But when you have these measurements or non-unitary evolutions, there isn't a strict light cone, okay, because of this problem of spooky action at a distance. But actually, one of the things that we did in our paper is that we figured out a way to to come up with a measure of information spreading that, this usual picture of how an operator grows in time doesn't really work once you have projective measurements. You can't just look at this Heisenberg picture, but we figured out a new way to kind of probe how information may spread in time, even for non-unitary evolutions where things like OTOCs are hard to define. And using this measure, we find that there's still a statistical light cone, okay? So even though you can have these rare trajectories where information is transmitted completely non-locally, statistically, you'll still get an emergent light cone in these dynamics. So there is still a notion of locality. Good. And finally, as I mentioned, one way in which we understand this volume law phase is as a novel kind of error correcting code, right? And the properties of this code depict CFT scaling at this entanglement phase transition. So we're starting to do various pieces of work in trying to understand the properties of this new error correcting code, which is quite different from all the codes that have been studied in the quantum information community. So this we understand very little about it so far, and I won't tell you much more than the fact that this is an open and exciting question. Okay. So let's get started. And to start, I'm just going to begin with this issue of measurement only models. Okay, so are there any questions before we, let me pause for a minute before diving in.
No questions.
No new questions.
Okay.
So
okay.
far.
Okay. Good. So let's go to let's come back to this picture of hybrid circuits where you have unitary evolutions interrupted by non-unitary measurements, right? So as I mentioned to you, one appealing picture for why you get a transition, right? It comes from the notion of scrambling of quantum information under the unitary gates. If the information is hidden in very non-local degrees of freedom, then if you go in and make local measurements, those measurements don't really access much information about your state, okay? So one appealing picture for this transition is to get an entanglement phase transition by equating some rate at which you're producing scrambling, right, or entanglement, which is this unitary, under the unitary dynamics, with some rate at which you're decohering your system or degrading your entanglement, which comes from the measurements, okay? So this is just, this picture will turn out to be wrong, so don't take it too seriously, but that's kind of one kind of intuitive picture for what might be going on, okay? But this picture then immediately begs the question, which is, how scrambling must your unitary evolution be, right? How scrambling must the dynamics be? If you just have a completely random unitary circuit, then we know that causes entanglement to kind of grow linearly in time, and you're also coming in and making measurements at a finite rate in time. So that makes sense that those can be equated. But what if my scrambling was slower? Okay, so one motivation that we had for asking this question is, suppose we considered scrambling in many body localized systems, right, where we know that the scrambling of quantum information is only logarithmic in time. Can we still get an entanglement phase transition if you have an MBL system that's subject to these local projective measurements, okay? So surprisingly, we found that the answer was yes, And actually, we were able to push this even beyond just the usual MBL systems, which have logarithmic scrambling, and consider a class of kind of MBL circuits where there was no scrambling whatsoever. Okay, so one picture of the MBL transition, and you know, I'm if you haven't heard this, don't worry, right? But it's this picture of L bits. So you have this phenomenological model for many body localization, where you have local integrals of motion. These local integrals of motion have exponentially decaying tails. Your Hamiltonian is diagonal in terms of these emergent new degrees of freedom, and these exponentially decaying tails are what lead to logarithmic increase in entanglement in time. Okay, so here we have a very simple toy model for this L-bit evolution, and we're just gonna pretend that this is all there is. Okay, so we're gonna work directly in this L-bit language, if you will. So these are these CZ gates. Okay, so these just look like these Ising interactions, and we're going to plop these gates down, right? And they're going to be a finite range. And then you also have these local one-site phase gates. Okay, so these are again diagonal on the Z basis. So that's the entire unitary portion of your evolution. You're just plopping down these finite range CZ gates and local Z rotations. Okay. So obviously there is no scrambling whatsoever under these dynamics, especially because the gates are finite range. If the gates had, if you put down exponentially decaying, if you put down long range gates with some exponentially decaying probabilities, then if you started with an X product state, you could still get some growth of entanglement through some dephasing. But here these gates are finite range. Okay, so the steady state that you'll get is area law entangled for p equals 1, which is or for p equals 0, which is no measurements. And then we come in and we put down kind of local measurements with some probabilities. Okay, so we'll put down measurements in the X basis and the Z basis, and these can be made with rates PX and PZ. Okay, and that's the setup. So in this particular problem, both when you have no measurements and when you have measurements all the time, you have an area law entangled phase. The surprising thing we found is that actually, if you move away from these p equals 0, p equals 1 limits, then you can actually get a volume law phase, right? And indeed, both the unitaries and measurements by themselves are limited to area laws, but the volume law exists because of the measurements rather than despite the measurements. Okay, so this is kind of more measurement enabled entanglement, because if we didn't have any of these measurements, you wouldn't get this volume law phase at all. So again, we're talking about strictly local one-site measurements and this kind of strictly local circuit with no scrambling whatsoever, but the combination of these elements together gives you a volume law phase, okay? And the way in which we understood how this happens is by actually taking this particular circuit and mapping it to one of these measurement-only problems that I was telling you about, okay? So how do you do that? So one thing you can do is kind of slide a gate past a measurement, okay? So what I was telling you is that when you go in and you make a measurement on a state, we're not going to average over measurement outcomes. So if you're going to measure some operator O, you basically project onto this. Here we're considering O's, which are going to be Pauli strings. So the expectation values of O's, the possible eigenvalues, are just plus or minus 1. So you pick a particular outcome, which is either up or down, right? Or plus 1 or minus 1. And you project your state onto that outcome, renormalize it, okay? But then what you could do is instead of measuring this operator and then acting with a unitary gate, right? Or acting with a unitary gate and then making this measurement, you can reverse this order, okay? And the cost of reversing that order by all I've done here is added this U dagger. The cost of reversing that order is that you make a measurement of an operator that has grown a little bit, right, under this gate, and then you act with the gate, okay? So for the particular L-bit circuit that I told you about, because these gates are strictly non-scrambling and strictly local, okay, all the X and Z measurements, they only grow by a finite amount by sliding this unitary past them, okay? So what you get in general is you have X's and Y's, and it can pick up tails of sigma Z's on either side. This is how operators spread under these L-bit dynamics. So you have these finite range operators, and you can keep sliding the unitary gates past, okay? And these gates all commute with each other because again, it's just trivial Z gates. So you can do this throughout. And then what you're left with is these kind of finite range, but more non-local operators. And then all your unitary gates have been compressed down to one circuit, okay? One layer. And this layer is non-scrambling, as I told you, right? Because it's just finite range. So from the point of view, whether your late time state is area law, volume law entangled, this layer makes no difference at all. Okay, so we can just forget about it. So what this brings us to is this class of measurement only dynamics, where I have this ensemble of operators that I'm measuring. I'm going to put different operators drawn from this ensemble down at different rates. And now I can ask, can I get different kinds of interesting phases? Okay. So that's the rule of the game. Let's just pick some set of Pauli strings, okay? O alpha, they have some probability distribution, which says that with probability P alpha, I will draw an operator O alpha from my set. At a given time step, you draw this state, and then you plop your measurement down, okay? So this is like this game of quantum Tetris, because you just pick your different blocks, these are your measurements, and you plop them down. And we don't have to do this, but it's convenient to kind of assume locality and statistical translational invariance. Okay, so this is this huge space. Okay, even if you fix the range of operators that you're drawing at some finite range R. Okay, there are 4 to the R minus 1 different species of Pauli strings that exist in that space of range R. So if R is 2, you can have XX, X1, YX, YY, right? All of these different strings. Each of those could have some probability, okay? And then you get this huge multi-dimensional space that's just really hard to track, okay? So to simplify this, we can consider factorizable models, right? Where we say that you only have kind of 4 probabilities to keep track of, which is the probability with which you get X, Y, or Z. And then if you have a given Pauli string, which has some string of X's, Y's, and Z's, you can say that, the probability with which that string is drawn is kind of a product of these individual probabilities. Okay, so this is more just for ease of cutting down this parameter space. So we did this, and we did this for a particular range 3 model. We've played with the range. You can do all of that. This is just for illustration. And if you don't allow identities, so you have all Pauli strings, which look like some products of X's, Y's, and Z's, then as a function of this parameter space, right, which can be represented as a triangle because these probabilities have to add up to 1, you find that, at the corners of these spaces, okay, so again, there are no unitaries here. So at every time step, I am making a measurement for sure, okay? So there's no unitaries. So what QZ equals 1 means is that all the measurements that I'm making are going to be strings of sigma z's. Okay, so that's what QZ equals 1 means. What QX equals 1 means is that all the measurements I'm going to make are range 3 strings of sigma x's. Okay, so here you can understand why this will give you an area law phase, because you have some initial state, you measure z z z z z z z z z z z everywhere, right? And that just gives you, that collapses you onto the simultaneous eigenstate of all of these z's, which is an area law state. But now, as you move away from these corners, okay, so now you're measuring operators like ZZZ, ZXZ, ZYZ, and these operators don't all commute with each other, okay? So it's now you can't simultaneously know the expectation value of ZZZ and then XYZ at with some overlapping set. And this causes what's known as kind of a frustration in the measurement ensemble. And this frustration actually can drive this phase transition into this volume law phase, okay? So again, I won't go into details here, but when we did the numerics, we actually found that the scaling at this entanglement phase transition, which can be diagnosed in various ways, was again compatible with this conformal field theory scaling that had been seen for various unitary measurement models. Okay, so here it's not at all clear what sort of some effective stat mapping would be, because you had this model of just plopping down measurements, and if you see evidence for some CFT scaling, that indicates there could be some underlying stat mech model, but we don't know what that is. Okay, so as I was saying, what's driving this kind of transition is In the unitary projective case, we had scrambling and unscrambling that was separated into two different processes, which were unitary gates and measurements. And this was kind of independently tunable because this measurement rate P at which you were putting down these non-unitary measurements was driving the transition. But in this measurement only case, the separation between scrambling and unscrambling is impossible. And measurements are doing both in a sense, okay? And the way we want to sort or organize these dynamics is in terms of something known as the complexity of the operator ensemble or the frustration of operator ensembles. And it's not, we don't know yet how best to define this, okay? But one thing that, here's a simple example that I just alluded to. So if all these measurements commute with each other, so say they're all sigma z's, okay? Then the steady state is a simultaneous eigenstate of all of these local measurements, and you get an area law phase, okay? But in the other limit, which is sort of most complex, if you will, if you can draw any Pauli string, suppose it's a global Pauli string on the entire system, there's 4 to the L of these with equal probability, right? And each new measurement has an equal chance of either commuting or anti-commuting with the prior measurement, okay? So you have equal probability of either gaining some new information about the system or not. And this is kind of the most complex, the most frustrated that you can get, okay? And so we want some paradigm, some way of kind of organizing this frustration. And one of the things that we played with is this notion of a frustration graph, okay? So here, what we did is that the operators that are in your ensemble are the vertices of this graph. So if on a given site you're measuring 2 species of operators, A and B, then those exist as nodes, and the edges between those nodes represent whether those operators commute or not, okay? And for this kind of Clifford evolution that I was describing to you, this frustration graph completely determines the dynamics or the entanglement phases. This is all you need to know about the problem, okay? So if you have different types of, so people have studied various types of these models in the literature, and if you have different ensembles of operators that have the same frustration graph, then they actually will have the same phases, okay? So now we've kind of reduced this problem of characterizing the frustration of our operator ensemble to some features or some properties of this frustration graph. And we don't know exactly what the best features of this frustration graph could be. Naively, you would think that, the more lines that you have, the more connected you are, the more kind of non-commuting your whole graph is, right? And maybe that's the worst that you can get, right? That's the most complex. But this is not obvious, because as I was telling you in the beginning, there's this class of graphs, which are these so-called bipartite graphs. Okay, so that's like, I have 2 species of operators, for instance, A's and B's, and all the edges in the graph are only connecting A's to B's and not A's to A's or B's to B's, okay? So whenever you have a bipartite graph, what we ended up finding, and this is a numerical observation that we verified for a huge class of models, so so we don't have a proof yet, but what we saw is that for this class of bipartite graphs, we always got a transition between 2 kinds of area law phases, okay? So for instance, suppose you have operators that are drawn from 2 different stabilizer codes, okay? So suppose you have the toric code for which all your stabilizers are mutually commuting, and then you have a different quantum code, say the double semyon code, for which all your operators are mutually commuting, okay? And you draw your operators from either A or B, but with some probabilities PA and PB, okay? Then as you tune this relative ratio of PA and PB, we find that in the A code, all the A operators commute with each other, and there's an area law phase deep in, when B is 0. In the B code, again, that's true. And as you start introducing these non-commuting operators, you actually maintain an area law phase, except at the self-dual critical point, okay? So this is just so it's almost like this meta notion that to get a volume law phase, you need frustration in this frustration graph, okay? It can't be bipartite. So this is all I want to say for now about these measurement only models, in which is that the driving principle is this notion of a frustration graph. It's still very open as to what features of this frustration graph are most important. And for this class of bipartite frustration graphs, you can actually get transitions between different area law phases, okay? Good, so now I'm gonna move to the second part of my talk, which is this issue of post-selection. Are there any questions so far?
Nope, people seem to be following.
Let's check, no, yeah. Mm-hmm.
Great. Good. So let's now switch gears a little bit and ask, how do we actually measure this experimentally, right? Is there any hope of detecting these kinds of new hybrid phase transitions, right? So as I told you, there's already experiments in, yeah.
There's an incoming question.
Okay, yeah.
For this type of models, does the statistics of the measurement outcomes provide any useful information?
Yeah. So that's right. So that's very classical, right? That's a classical measurement record. So the quantum information is hidden in your quantum state, but this hasn't been done yet, but people have been thinking about whether looking at the entropies of those measurement records itself can give you some useful information. But that's not an answered question, but people are thinking about that.
Okay, and then there's another question. Do these measurements only results hold for Pauli measurements or even for arbitrary POVMs?
They hold for arbitrary POVMs as well. And in fact, the next part of my talk is going to talk about arbitrary POVMs. So a POVM is a positive operator value measured. So that's a weak measurement where you're not definitely projecting. It's not a projective measurement, but a weak measurement. And as you tune the weakness of this measurement, you can get phase transitions too.
Okay, thanks. There are no more questions right now. So
okay, good. Right. So you want to ask, how do we detect these transitions? Now, measuring the entropy by itself is extremely hard, right? That's already a very challenging problem, but Greiner's group made some progress on this. They did those experiments that I showed you previously. They also did some experiments that I was involved in where they were actually measuring entanglement dynamics across some kind of putative MBL transition and seeing different behaviors. So this there's already progress on, despite the fact that it's hard. Now, in measuring entropy, the most accessible entropy is the second Rayleigh entropy, right? Which is related to the purity of the system. The purity is trace of rho squared, and this is e to the minus S2. S2 is the second Rayleigh entropy. But what this requires is producing kind of two identical copies of this state. Okay, so any kind of measurement of entanglement or other observables. Peter, you're frozen. Am I frozen?
No,
I think you're good. Yeah.
Okay. So any kind of measurement of either the entanglement or any observables requires you to prepare multiple copies of the same state. Okay. So there's some challenges to this, which just come from unitary control errors, right? You have to run the exact same circuit over and over again to get multiple copies of the same state. But let's just assume that we're perfect experimentalists and we can get rid of this unitary control error completely. Okay. Even with that, once you have these projective measurements, this quantum randomness of measurement outcomes makes this an exponentially hard problem to reproduce the same state. Okay, so again, consider two runs A and B. By perfect experimental capabilities, I have made it so that the unitary gates between A and B are identical. And I also put down my measurement apparatus and make measurements at exactly the same locations in the evolution. Okay. So say in the first run, I make these measurements of the sigma z basis and I get, up, down, down. Now I do it again, I get lucky, I get the same outcome for the first measurement, I get lucky, but then eventually I'm going to run out of luck. And just by sampling with these Born probabilities, I'm going to get a different outcome. Okay. And if this happens, then I just have to throw this run away and start over again and keep doing this over and over and over again until by chance, this run B gives me the same outcomes as run A. Okay, so this is this problem of post-selection, that you select after you've seen these outcomes. And this gives you this exponential overhead in the number of measurements made. And if you have this finite rate of making measurements, the number of measurements made is going to scale with both the size of the system and the time to which you go. So this just becomes this impossible problem. Okay, so there are some ways around this limitation, right, of this post-selection. One interesting thing that was there in this paper by Gullins and Hughes was to probe this entanglement phase transition using a local order parameter that coupled to a reference probe. Okay, so I won't go into this, but they basically diagnose this transition by looking at the properties of some reference probe that was coupled into the system, okay? The other thing is to just do kind of classical simulations. If you look at Clifford circuits, then you can kind of you can correct for, it's almost like an error correction, where if you get the wrong measurement outcome, you can apply a unitary gate that will fix it, and then you can keep going, okay? So this is fine, but we do have this, we do want this access to, instead of looking at this indirect local order parameter or this class of Clifford circuits, there is, of course, this desire to more directly access the dynamics of entanglement, like the actual entanglement of the state for evolutions that are non-Clifford, okay? So how do we do this without getting into this problem of post-selection? So we don't have a completely general answer to this. I don't think you can give a completely general way around this problem, but what we've shown, and this will appear tomorrow, is that for a broad class of non-unitary circuits, which are space-time duals of unitary circuits, I'll explain what that is in a second, okay? There's a protocol for directly measuring the purity or the entanglement entropy of the state as a correlation function of an associated unitary evolution, okay? So even though you're doing this non-unitary evolution, you can map this entanglement properties to a correlation function in a unitary evolution, okay? So and this is a new class of dynamics that I'll just describe to you, okay? So what is space-time duality? So it's very simple. It may sound fancy, but it's really simple. So imagine you have some gate, okay? And if I'm viewing my circuit vertically in time, so time runs up, okay, then you have two input legs, I1 and I2, and you have two output legs, okay? But now I can actually view this gate not with time going upwards, but with time going from left to right, okay? So it's just a rotation of my space-time axes. And this gives me this different matrix U twiddle, okay, which is just a permutation of the entries of U, okay? And let me show you an example. So if your unitary is the simplest unitary you can imagine, which is just the identity, okay, then you had all ones here, right? And this was represented by these whirl lines just going up in time. But now, if you want to get at the new matrix U twiddle, which is the identity viewed on its side like this, okay, then you're going to end up permuting some of these entries. That permutation, take my word for it, looks like this, okay? And this is a rank 1 matrix, and this is actually just a projector onto this Bell state, which looks like up, up, plus down, down, okay? So in whirl lines, this is represented, if you view this from the side, as you have two qubits, they're annihilated by this measurement outcome and then reinitialized in this Bell state, okay? So what this means is that dualized gates are generally not unitary, right? I took the simplest unitary gate, which is the identity, and when you view its dual, then you actually get this non-unitary projective measurement onto this Bell state, okay? They need not be forced measurements. The example that I gave you was a projective measurement, but in general, this is connected to this question of POVMs. You can get weak measurements, okay? So you will get some non-unitary gate most generally, and this will represent a weak measurement. And the key is that it will represent a forced weak measurement, okay? So here, of all the 4 possible Bell states that I could have had, this is always picking out this particular Bell state, which is up, up, plus down, down, okay? There's no other option that is being presented. So this is a forced measurement outcome. So it gets rid of this Born randomness, this randomness of measurement outcomes. And that's the key, okay? So that's the class of circuits we'll be considering, which are going to be viewed as space-time duals of unitary circuits. And we'll go from there, okay? I want to mention that this notion of space-time duality has actually been used recently in various contexts, okay? So there's this particular class of dual unitary circuits, okay? So those are unitary gates that are that map to other unitary gates, okay? So these are very special class of unitary circuits. And it was shown in Tomasz Prozin's group recently that in this class of circuits, you can actually give a derivation of the emergence of many body quantum chaos starting from very microscopic models. Okay, so this was a really, really cool result. And it also gives you analytic control over correlations, out of time ordered commutators. So you can get a lot of mileage out of these dual unitary circuits. We're going to be considering non-unitary circuits. And in the kind of quantum computer science end of things, there was a paper by Aram Harrow from early this year, where they actually used this trick of viewing a circuit not in time, but kind of in a flipped over direction to optimize kind of tensor network contractions and to provide some results on the simulability of circuits. Okay, so this idea of flipping space and time or mixing between space and time is very useful and has been used in a variety of contexts.
So there is a related question actually in the chat.
Yeah.
In which so the question is, does this space-time duality, is this space-time duality a mathematical construct, or if there is some physical intuition I am missing?
So I think for now it's mostly just a mathematical construct. It's a particular class of evolutions that you can consider. In Tomasz's case, it was a particular class. It was a very restricted subset of unitary evolutions. In my case, it's going to be a subset of non-unitary evolutions, which are duals of unitary evolutions. But if you can get the hope would be that you can use these models to glean some features that would then be universal or then shed some light. So in Tomasz's case, it was how do you get these random matrix statistics? And the hope is that those would be more general than the particular model that you used for solvability. Yeah.
Got it. Thank you.
Okay. So good. So under these so what are we going to do, right? So we're going to study purification dynamics. Okay. So this entanglement phase transition that I had told you about actually also maps onto what's known as a purification phase transition. Okay, so instead of starting with a pure state, you can start with the fully mixed state, which is, say, the identity in this diagram that's represented by these gray lines. Okay, you can act on it with some circuit, which is M. This is generally going to be non-unitary. And under this circuit, your output state just goes as M rho n M dagger. Okay, if the rho n is identity, this is just proportional to M and dagger. Okay, so of course, if M was unitary, all of this would cancel and you would just be you would get back the identity. But when M is non-unitary and you're making all sorts of measurements, those measurements keep getting some information about your state, and so your state purifies in time. Okay, the purity again is just, so now I'm considering the system as a whole. The purity is given by the trace of rho squared, which is related to the second Rayleigh entropy. And what this paper by Gullens and Hughes showed is that if your system under these non-unitary dynamics purifies in a time that was logarithmic in L or order 1 in L, then you get then that's same as the area law phase of pure state dynamics. But if it takes a much longer time, like exponential in L, for the measurements to gain information about your system, then that's like the volume law phase in the pure state dynamics. Okay, so we're going to consider the purification dynamics of these mixed states. And, so this is just, I'm just redrawing this picture. So that was rho squared. Okay. Oh, sorry, that was rho. If I'm looking at trace of rho squared, that's this diagram. So I just make two copies of rho. So that's rho and rho. And then this trace of rho squared is these contractions here. Okay. So this is the diagram for trace of rho squared. And then I haven't done anything fancy here. I've just kind of unfolded this and flipped it, okay? And that's what this picture looks like. But now this is this, this picture where, the unitary was being fed in here from the bottom. Now the identity was being fed in from the bottom. Now the identity is being fed in from the side, okay? And this evolution here is the space-time dual of whatever non-unitary evolution I had there, okay? And if I pick particular non-unitary evolutions that are dual to unitaries, okay, so this will not be true of a non-unitary evolution in general, but if I pick non-unitary evolutions that are dual to unitaries, then what I find is that, I have this evolution where I have unitary evolution on this left half, unitary evolution on the right half with a related unitary circuit. This R refers to a reflection, and the only non-unitary stuff is something in the middle here. Okay, these are these horizontal lines. So what that means is that this purity of the hybrid circuit M gets mapped to a correlation function in this unitary circuit, and the correlation function is for a weird multi-point operator that involves these lines here. Okay, so can I get 5 minutes? Yeah. Okay.
Sure. Go ahead.
Good. So all right. So what's happening here, right? Okay. So So we had these identities everywhere because, and the only non-unitary stuff in this new diagram is in the middle there. Because these blue and red boxes are unitary when viewed in this direction, okay, you can actually perform all these tensor contractions, and U meets U dagger, and everything gets elided, right? So that's why you get this effective light cone that emanates from this non-unitary, these operators in the central bond. Everything else just contracts away to the identity, okay? So you have these qubits in the central bond. Remember that the dual of the identity, when viewed this way, was this forced Bell measurement, okay? So in this protocol, the qubits in the central bond are initialized in this Bell state, which is up, up, plus down, down. All other qubits are initialized in this fully mixed state, okay, which is just the identity. Then you run your circuit, right, where you're acting with these unitary gates. And then at every time step, you make a Bell measurement on the central bond. Okay, so that's what you're doing. So you're only measuring the central bond and you're acting with unitaries everywhere else. And then at the end of your protocol, you make a Bell measurement again of the central bond, and everything else is just traced out or discarded. Okay, so what this tells us is that, and in practice, the protocol is that we initialize this state, which is identities everywhere, bells in the center, and then you make these Bell measurements everywhere. Anytime a measurement gives you the wrong outcome, which is it gives you 0, you stop and you record a failure, okay? But if it keeps giving you, if it gives you the right answer, then you keep going, okay? So a success is when you go till time t, if you end up with t consecutive Bell measurements that gave you 1, okay, that's a success, okay? So you record your failures, you record your success, you run your protocol n total times, many times, okay? And you count the number of successful runs up to time t, okay? And what you find is that the purification, so I'm not going to be able to get into the details, but the purification of these 2t qubits, so again, so this dual direction is this time running horizontally, and you're running this for time t, 2t qubits, okay? So the purification of this mixed state, which lives on this time-like slice here, because you're coming at it from this side when viewed for the non-unitary dynamics, ends up being mapped to this, it is exactly given by the ratio of the number of successful runs to the number of total runs, okay? And what this means is that in most cases, okay, you actually expect that you'll end up getting something that's a mixed phase, because you expect that the number of successful runs is going to go down exponentially in time, right? Because even if there's any non-zero probability of measuring something that is in the Bell state, then to get t consecutive measurements, which are all the Bell state, is a probability that's exponentially decaying in time. So you measure this kind of multi-point correlation function, which is just keep doing these measurements, you get something that's exponentially decaying in time. But then the time constant with which it decays is exactly equal to the entropy density, or to the entropy of your mixed state under the hybrid evolution. Okay, so this entropy density is directly measurable using the time constant of this exponential decay of this correlation function. Okay, and the key point is that this protocol does not use post-selection, okay? Because even when you get a failed run, it actually contributes to n total and gives you information, right? It's not that you throw away the failed runs, you keep track of when your run failed, and that enters this denominator here, okay? So this forward unitary evolution automatically prepares 2 copies of the same state when viewed sideways, okay? And you get this very simple result between the purity and these measurements in the middle, okay? So of course, this is not an answer for completely general non-unitary evolutions, okay? But it is still a wide class. It's a space that's as big as the space of unitary circuits, because for any unitary circuit, you can look at its dual. You'll get some general non-unitary circuit, which represents some POVM process, okay? And for those circuits, you can ask about entanglement dynamics, you can ask about all sorts of different questions. And here, so this is opening up this space of studying all sorts of properties of non-unitary circuits that are dual to unitary circuits. And one simple thing that I'm telling you about this is that this gives us a way to measure entanglement properties without post-selection, okay? This state that you're interested in is prepared on this temporal slice, not on a spatial slice, but actually there's a state preparation protocol that you can do if you want to, if you're just interested in the state itself, because it could be an interesting state, there's a state preparation protocol you can do to actually get it in space also. Okay, so I won't go over, so this was just showing you that you can get different types of these purification phases in these hybrid circuits. Let me not get into that, and let me just summarize by saying these kinds of monitored non-unitary evolutions is a vast new arena for many-body dynamics. Some of the things that I told you are that these measurement-only models furnish a new example of dynamical entanglement phase transitions driven by the frustration of measurement ensembles. You can get a statistical light cone for information spreading, even under your non-unitary dynamics. You have this dynamically generated quantum error correcting code with various novel properties. And then if you have space-time duality that gives you this class of non-unitary circuits with forced measurements that sidesteps this issue of post-selection and more generally gives you this class of dynamics that we can explore all sorts of other questions. Okay, so let me stop there. I'm sorry for going over.
All right, thank you very much, Vedika. That was great. So we, well, again, we encourage people to ask questions. There was a question just by the end, but I think it was kind of already addressed. I'll just mention it kind of, I was thinking about a similar thing. There was a question about how this procedure that you were describing at the end was different from post-selection. And it was basically one of your last slides. So it seems like, I mean, it's correct that even the runs that you are discarding give you important information to estimate what you want to estimate.
Exactly. So this is the, so this is the formula, right? So,
right.
So this is the number of successes, but the number of failed runs enter the denominator. So no information is, so the failed runs enter the denominator, and that's what gives you this. This will generally be exponentially decaying, but right. That exponential decay is the probability of failure, right? So you're actually using that exponential decay instead of throwing away that exponential and then and then extracting the entropy density from that decay constant.
Got it. So, well, there are comments in the chat thanking you for the talk. I might wait a minute or two to see there are more questions. I had one actually, which it was related to one of the questions that was asked during the talk about the information that you get from the measurement outcomes. Mm-hmm. And I mean, there is no, well, you mentioned feedback at some point in the talk, but I was just wondering when you were talking about the complexity of the ensemble of operators that you're measuring, could it be possible to think about using the information that you get on the measurement outcome to condition what you're measuring afterwards to maybe with this kind of control the complexity of the ensemble of measurements that you're doing?
Yeah. So that would be right. So let me give two answers to that. So one is, if you're talking about these post-selection problems, right? If you're doing Clifford dynamics, then this is not really a problem because, if you get the wrong outcome, you can very easily fix it. So if you're doing measurement only dynamics where we're only measuring Pauli strings, we don't have to do that, right? Then this issue of post-selection isn't really a problem. But to answer your question, so this is indeed something that I've thought about, but I haven't done anything on. Is instead of having random and time dynamics, right? So where every outcome is just completely independent. If you had some kind of correlations in time where you act with something and then your next outcome is conditioned on that in some way, then based on the strength of those correlations, can you get some kind of novel transitions? And I don't know the answer to that. One thing I'll say is this trick that I told you about sliding all the unitaries past to get kind of this measurement only model for the L-bit model, that already gives you measurements that are correlated in some way. Rather than being completely random, but using that as an explicit tuning parameter, I think was a very interesting question. And you know, lots of, yeah, I don't know what to get. Yeah.
Thanks.
Yeah.
All right. It seems there are no more questions in the chat. But we had plenty of discussion throughout the talk. So then let's thank Vedika once again for this great talk. We'll just, yeah, our pleasure. We'll just announce next week's seminar real quick. So next week, we'll have Bing Yan from Los Alamos National Laboratory, and we'll go back to the usual time of, you know, whatever it is, 9 a.m. Mountain, 5 p.m. in Germany or something. And the title of the talk is the quantum zoo of butterflies. So that should be interesting. So with that, thank you again to all of you for tuning in, and